Assalamualaikum, my name is Iman Suhairi bin Muhammad Khairul Saleh, number matric B122510170. Today, me and my team are going to represent our project for BRE2353 electronic system. First of all, let me introduce our team members. First is me, Iman Suhairi bin Muhammad Khairul Saleh. Second, Amirul Amma bin Razali. Third, Maryam Mahfuza binti Mazlan. And lastly, Nuris Eliyin binti Faizal. Introduction. This project focuses on designing and simulating a complete electronic system that converts a mixed analog signal into a stable 5-volt DC output. Two Windbridge oscillators generate sinusoidal signals at 1 kHz and 20 kHz, which are combined and passed through a second-order Sallen-Key Butterworth low-pass filter with an 8 kHz cut-off frequency to isolate the 1 kHz signal. The filter AC signal is then converted into DC using full-bridge rectifier and 1 microfarad capacitor to reduce ripple. Finally, an active shunt voltage regulator stabilizes the output at 5-volt DC to safely power a 25 ohm resistive load. All calculation and multi-sim simulation consider non-ideal component characteristics, including a 0.7 diode forward voltage drop and 0.7 voltage transistor-based emitter voltage to ensure realistic system performance. The objective of the project assignment is first to design and simulate a multi-stage electronic power system capable of generating, mixing, isolating, and converting. Second, to simulate the complete system in order to evaluate its performance and functionality. And the third, to analyze the output waveform and confirm that the intended signal processing is successfully achieved. Oscillator 1. Oscillator 1 is designed as a Windbridge oscillator running on a 15-volt split DC power supply, specifically engineered to generate a clean, stable, sinusoidal reference waveform at a target resonant frequency of 1 kHz. Structurally, the circuit relies on a lead-like RC feedback network containing a 10 kilo-ohm resistor and 15.915 nanofarad capacitor to precisely dictate its operational frequency. To sustain self-starting oscillation without clipping the output signal into a square wave, the non-inverting operationally amplifier configuration maintains a closed-loop gain slightly greater than or equal to 3. This condition is carefully balanced by setting the feedback resistor R1 at 20 kilo-ohm against an input resistor Ri1 of 10 kilo-ohm, ensuring a reliable low distortion 1 kHz fundamental AC frequency before it is mixed and forward to the subsequent filtering stage. The two pictures under is a simulation of oscillator 1 and the schematic circuit of oscillator 1. Calculation of oscillator 1. It is given target resonant frequency is 1 kHz and the DC supply voltage is 15 voltage. The calculation for capacitor is we are using the formula of resonant frequency, which is 1 divided 2 pi Fr resistor capacitor. Then change it to capacitor equal 1 divided 2 pi FRR. The value of frequency resonant is 1 kilo and the resistor is 10 kilo. The answer of capacitor is 15.92 nanofarad. Calculation for Rg and AV. Rf equal 20 kilo ohm and the Rf equal 2 Rg. So the Rg equal 20 kilo ohm divided by 2. We got 10 kilo ohm. For the AV equal 1 plus Rf divided by Rg. The value of Rf is 20 kilo ohm and the value of Rg is 10 kilo ohm. Divide it and plus by 1. We got 3.
Assalamualaikum. My name is Amirul Ahmad bin Razali. My matrix number is B122510183. Right now, I want to explain about oscillator 2. Oscillator 2 is designed as a wind bridge oscillator running on a 15-volt split DC power supply, optimized to generate a clean sinusoidal reference waveform at a high resonant frequency of 20 kHz. Structurally, the timing feedback network released on standard 10 kilo ohm resistor matched with 0.795 NF capacitor to achieve the precise target frequency. To guarantee stable, self-sustaining oscillator without causing signal distortion or clipping. The non-inverting operational amplifier configuration maintains a formal voltage gain of exactly 3. This gain requirement is satisfied by setting the feedback resistor at 10 kilo ohm and the gain resistance at 5 kilo ohm. The resulting high frequency 20 kilohertz AC signal is the combined with the output of oscillator 1 to produce the composite input waveform, schedule or subsequent filtering and regulation. Okay, this is the calculation of oscillator 2. For capacitor, Fr equals to 20 kilohertz, and the formula for Fr is 1 over 2 pi Rc, and the C is 1 over 2 pi FRR. So the C is 1 over 2 pi times to 20 kilo times to 10 kilo, and the result is 0.79 NF. For Rg, Rf equals to 10 kilo ohm, and then Rf is the 2 Rg. Rg is 10 kilo ohm divided by 2, and Rg equals to 5 kilo ohm. For AV is 1 plus Rf divide to Rg. So the AV is 1 plus 10 kilo ohm divide to 5 kilo. So the result of AV is 3. Then this is the active low pass filter. The active low pass filter stage in your system is designed as a second order Sankey low pass filter featuring a Butterworth response, which provides a maximally flat pass band to avoid signal distortion. It is configured with a precise cutoff frequency of 8 kHz based on your design calculation using a baseline resistance of 10 kilo ohm. The required capacitance is determined to be 1.989 NF to set the frequency boundary. Additionally, to establish the proper damping factor required for the Butterworth characteristic, the scaling resistor is calculated at 5.68 kilo ohm against a 10 kilo ohm reference resistor. The primary function of this entire active block is to receive the combined multi-frequency signal from the oscillator, allowing the desired low frequency 1 kHz signal to through cleanly while heavily attenuating the unwanted high frequency 20 kHz component before it reach the rectifier. Okay, so this is the calculation of active low pass filter. For capacitor, Fr is 1 over 2 pi Rc. For the C is 1 over 2 pi FRR. And then we combine it to 1 over 2 pi times to 8K and 10K. So the result of C is 1.989 NF. For R38 is R38 divide to R49 minus to 0.568 ohm. So the result is 568 kilo ohm.
My name is Maria Mafuza binti Mazlan and I want to present about full bridge rectifier. The full bridge rectifier convert the AC input into a pulsating DC output for diode. During operation, two diode conduct at a time, causing a total voltage drop of about 1.4 voltage. A 1 microfarad capacitor is connected across the output to smooth the DC voltage by reducing ripple before it enters the voltage regulator, which 215 load and 200 milliampere load current. The ripple voltage is reduced from about 100 voltage at 1 kilohertz to around 5 volt to 20 kHz, providing a more stable DC output. Next, this slide shows the calculation full bridge rectifier. First, we calculate the load current. The load resistance RL is calculated using the formula R equal V 2 divided by P. The result is 25 ohm. Then using I equal V divided by R, the load current is 200 milliampere or 0.2 ampere. Next is the ripple voltage calculation. The formula used is V ripple equal L load divided by F times C, where C is 1 microfarad. For the first frequency, 1 kilohertz, the full bridge rectifier doubled the frequency to 2 kilohertz. Therefore, the ripple voltage is 100 volt. For the second frequency, 20 kilohertz, the output frequency becomes 14 kilohertz. The ripple voltage is reduced to 5 volt. From this calculation, we can conclude that a higher frequency produces a lower ripple voltage. This gives a smooth and more stable DC output before it enters the voltage regulator. Okay, the next slide is the operational amplifier, shunt voltage regulator and load. This is a final stage of the circuit. Its function is to stabilize the DC voltage and produce a constant 5 volt output. The circuit uses a 1N5221B Zener diode as a 2.4 voltage reference voltage and amplifier and operational amplifier to control the output voltage. A transistor with a 0.7 base emitter voltage drop help regulate the output. Finally, the circuit supplies a 5 volt output to a 25 ohm load, delivering 1 watt of power with a load current of 200 milliampere. Okay, this slide show the calculation for the operational amplifier, shunt voltage regulator and load. First, we calculate the output voltage V out. The formula used is V out equal VZ 1 plus R1 R2. Since the Zener voltage is 2.5 volt and R1 equal R2, the output voltage is 5 volt. Next, we calculate the resistance value. R1 and R2. Based on the formula, R1 is equal to R2, so both resistor value are chosen to be 10 kilo ohm. Then we calculate the voltage drop across the diode. Each diode has a forward voltage drop of 0.7 volt. Since two diodes conduct at the same time, the total voltage drop is 1.4 volt. Finally, we calculate the load resistance using the formula RL equal V squared divided by power, which an output voltage of 5 volt and a power of 1 watt. The load resistance is 25 ohm. From this calculation, we can confirm that the regulator provides a stable 5 volt output with a 25 ohm load, which meet the design requirement.
My name is Nourish Lee binti Muhammad Faisal. My metric number is B122510.82. So now let's look at the full connection of each block as shown in image. This slide represents the complete end-to-end integration of our electronic system, cascading all 5 functional blocks to transform multi-frequency AC signal into a stable DC supply. To summarize the complete signal flow, first, mixing stage. The output of our 1 kHz and 20 kHz wine bridge oscillator are first mixed together to form a complex multi-frequency composite waveform. Number two, filtration. stage. This mixed signal is fed into the second order silent key active low pass filter LC equal 8 kHz, which precisely isolates the 1 kHz fundamental frequency and attenuates the unwanted 20 kHz interference. And the third is conversion stage. The filter AC wave pass into the full bridge rectifier, converting it into a pulsating DC signal that is pre-moved by parallel 1 microF capacitor to minimize voltage ripple, and the last regulation state. Finally, this volatile DC signal is processed by an op-amp shunt voltage regulator utilizing a YN5221B Zener diode reference. Despite non-ideal semiconductor drop, the control loop successfully clamps the output to deliver a rock-steady 5V DC supply across the terminal 25 ohm resistive load, perfectly fulfilling our 1W power delivery target. Assalamualaikum, my name is Nourish Ilya binti Muhammad Faizal. My metric number B122510182. So now we move on to the discussion section focusing on two main stage. First, under signal generation, we designed a dual source network using two independent wine bridge oscillator in multi-zone. Oscillator 1 generates a clean 1 kHz sinusoidal signal to act as our fundamental AC source. Oscillator 2 acts as a high-frequency noise source at 20 kHz to simulate real-world interference. Combine this provide our multi-frequency composite input. Second, for signal conditioning, we use an active second-order Selenke low-pass filter with a cut-off frequency of 8 kHz. This filter acts as a gatekeeper. It allows our essential 1 kHz signal to pass through safely. At the same time, it heavily suppresses the unwanted 20 kHz high-frequency noise. And ultimately, this isolates a clean, high-quality AC sinusoidal wave before it moves into the power conversion hardware. Next, we move on to the final two stages of our discussion. First, under power conversion, the filter AC signal is converted into U7 DC using 3N24 full bridge rectifier. First, the diode matrix flip the negative half of the AC wave to create a single polarity pulsating DC signal. Number two, to make the design realistic, we account for non-ideal semiconductor constraint, noting a total path loss of 1.4 V due to the 0.7 V drop per diode. We then integrate a parallel 1 UF smoothing capacitor across the bridge node to flatten out the raw pulsation and significantly reduce peak-to-peak ripple voltage. Second, for power regulation, we address voltage stability using an active op-amp driven shunt voltage regulator. This regulator uses a stable Zener diode reference and an evenly matched feedback voltage divider network R21, R22 to 1K. This control loop clamps the unstable DC input into an unyielding flat 5 VDC output. Ultimately, the unified system successfully delivers a rock-steady, ripple-free 200 mA drive current into a 25 resistor load, perfectly satisfying the request 1W power delivery specification. Finally, to conclude the presentation based on the summary, we have successfully designed, simulate, and integrate a multi-stage electronic system that effectively transfers a mixed AC signal into a stable DC power supply. To summarize our process, we establish a complex composite waveform using a 1 kHz line bridge oscillator and a 20 kHz noise source. A second-order Salem-Key active low-pass filter was used to precisely isolate the 1 kHz signal. This clean AC signal was then converted into a pulsating DC waveform via a full-bridge rectifier. Lastly, the signal was moved and tightly controlled using an op-amp driven shunt voltage regulator. Despite a real-world semiconductor loss such as the 0.7 Virginia entrance system dropped our control loop successfully clamped the final output to a rock-steady ripple-free 5 VDC. Ultimately, the system achieved its precise engineering target by delivering a 200 mA drive current across a 25 ohm resistive load, first satisfying the request when the power specification. That concludes our presentation. Thank you very much for your time.